Ice, ice, baby!
Hi, I'm Julia, the Principal Investigator of the Research Group for Shape-Dependent Electrochemistry, and welcome you to our new video series on mass transport phenomena in electrochemical impedance spectroscopy. The current, or impedance, that we can measure externally is determined by interfacial or near-interfacial electrochemical processes. Because modern EIS equipment allows system responses to be measured over many orders of magnitude of frequency, it is possible to obtain information about electrochemical sub-processes occurring at different timescales. I have chosen the Faraday reaction of a ferrocyanide redox couple in an aqueous supported electrolyte solution as an example. A crucial step in this electrochemical reaction takes place at the electrode-electrolyte interface. This means there is an electron transfer across the interface of an electron conducting phase to an ion conducting phase. The associated kinetically controlled current depends on the standard heterogeneous rate constant of the reaction K0, the reactant and product concentration C, the surface area of the electrode A, and is an exponential function of the applied potential E. Mechanisms for the sub-process and mathematical descriptions are provided, for example, by the Butler-Vollmer theory or the Marcus-Hasch theory. In EIS, the corresponding quantities available to us are called charge transfer resistances. They are ohmic in nature, but are potential dependent. As we apply a more negative potential to the electrode, a cathodic net reaction occurs and current flows through the interface, so that the concentrations of ferri and ferrocyanide in front of the electrode change. In consequence, the oxidized species is transported to the electrode, and the product species formed are transported away from the electrode to the bulk solution. Concentration profiles are formed between the electrode surface and the bulk solution, and diffusion occurs. Such sub-processes involving the movement of ions are generally referred to as mass transport. Different forms of mass transport can be distinguished by the type of gradient that causes them. Mass transport can occur due to a concentration gradient and is then called diffusion. It can occur due to a pressure gradient, convection, or to a gradient in electric potential, migration. These sub-processes can also take place simultaneously. A pressure gradient can be induced, for example, by stirring, which leads to forced convection. Migration effects on the redox probe of interest are usually avoided in electrochemical measurements by a sufficiently high concentration of conducting salt in the electrolyte. In this video series, we will focus on diffusion phenomena as described by Fick's law. We will look at different modes of diffusion, such as planar and convergent diffusion, and how they appear in electrochemical impedance spectra. In this introductory video, we recall some basics of semi-infinite linear diffusion of a redox pair in solution and get a first glimpse of the corresponding impedance response. It should be noted that there are many more complex electrochemical systems than this autosphere redox couple and a flat metal electrode. For example, batteries and electrolyzers. Similarly, there are many more electrochemical sub-processes than charge transfer and mass transport. For example, the transformation of the electrode materials themselves in conversion batteries or the adsorption of reactants on the electrode surface.
Hello everybody, my name is Kathleen. I'm a postdoc at the Shape-Dependent Electrochemistry group. Today I want to show you something more about linear semi-infinite diffusion. Therefore, we prepared a familiar experiment in form of a cyclic voltammogram. Experimental setup looks like the following. We have a beaker containing a solution of ferricyanate, each 50 millimolar, and supported by sodium perchlorate. In the front you can see the carbon rod counter electrode, and in the back you can spot a mercury sulfate reference electrode. For the working electrode we use a macro electrode containing platinum in a diameter of approximately 8 millimeters, which looks something similar like this gold electrode in my hand. Now let's move over to the PC and start the experiment and look how the cyclic voltammogram looks like. We start off the measurement with determining the open circuit voltage, at which then our cyclic voltammogram starts off. The scan rate is approximately 50 millivolts per second, and now we can see the forward scan where the current rises until it peaks and then declines. At the forward reverse potential, we enter the reverse scan, where we then see that in a similar manner the current declines steeply, peaks, and then raises slowly again. At the negative reverse potential of minus 750 millivolts, we then enter again the forward scan, and the whole cyclic voltammogram repeats. Again, we see the rise in the current, peak, and the decline. And why the shape looks like it does is something my colleague Oliver will explain you further at the whiteboard.
Hello. I'm Oliver, PhD student in the ShapeEC group. Now we want to have a look on why this kind of CV looks like it looks. So to understand this, first we have to have a look at the experimental conditions. First of all, we have to have a look at the macro electrode that we have used and how the diffusion layer formed at it. So our electrode here it's an embedded polymer, and if we now have electrochemistry going on there, we get a diffusion gradient right at the electrode, like this. And we have to consider that this gradient is quite small. It only extends for like 100 micrometers into the electrolyte. And this is quite comfortable if you want to depict this theoretically, because you can neglect what's going on here at the edges and just look at this part here in the middle, which has a linear behavior. You can just describe it by the distance x perpendicular to the electrode. Therefore, we call this linear behavior. There's a second comfortable thing about this. Since this diffusion layer is so small, it's not really important how far the electrolyte is going. We can always assume, as long as we have not some microfluidic system or something, that this can also go on forever or just a few centimeters. It doesn't matter. You can just describe it as a semi-infinite system. The semi comes from the fact that at one side it's just blocked by the electrode. We call this semi-infinite. And therefore the model that we use to describe this is called linear semi-infinite diffusion. And we also have to consider what's actually in our solution. We have two redox active species, one reduced and one oxidized species, and we have to consider the concentration of both. Let's depict it in dependence of the distance x that we already know. So here we depict for the oxidized species in red. The concentration is this, and we should have the very same for the reduced species. In solution, both are there 50-50. Now, these are the starting conditions for the experiment. So we are just at this point. Now, how does the concentration changes when we measure the CV? So, for the sake of simplicity, we start looking just at the reduced species to start. And now we just start increasing the potential, therefore forcing the concentrations to change right in front of the electrode. So, we do the same thing at this point here, drawing the same graph. We have still the same concentration in the bulk because the bulk concentration cannot be changed by the electrode. It doesn't work this way, but at the electrode it's significantly lower, and between there's also a layer where the concentration is increasing called the diffusion layer. That's the basic concept. So first see the current rising in this experiment, but at some point it's going down again. This is where the reduced species is depleted at the electrode, and the limiting factor at this point is how fast new reduced species can be transported to the electrode to support the oxidation reaction. If we are at this point here, shortly after the maximum, it looks more like this. So we have reduced species approaching zero, still normal concentration, the bulk concentration, and the diffusion layer increases. So the diffusion layer can be depicted by looking at the concentration gradient right at the electrode at this point, extrapolating it up to the point where it meets the bulk concentration. This point then describes the diffusion layer thickness, here depicted as delta. Following this definition, to be more precise, it's called the Nernstian diffusion layer thickness. So, as the experiment keeps running, then we are just flattening the concentration gradient right at the electrode. This also means that less of the reduced species reaching the electrode, therefore we see the current going down. Now, in this case, also the diffusion layer is rising, is getting bigger accordingly. So, now we have seen how the reduced species behave if you apply oxidizing potential, or a higher potential just. Now we have a look how the oxidized species it's generated at the electrode. Therefore, the concentration at the electrode is higher than in the bulk solution. Notice that its behavior is more or less mirroring the behavior of the reduced species. If we then would go to reducing negative potentials and start reducing the oxidized species, we would observe something similar like this, but vice versa. Now, this is basically shaping this CV into the shape as it has. It has a big diffusion influence on this experiment is very big. Now we can ask the question, what is the diffusional influence on an impedance experiment? Let's go into the lab and find out. Now, welcome to the lab, where we have the same setup as for the Cyclic voltammogram measurement. So it's the ferrocyanide couple in the sodium perchlorate solution, the carbon rod as counter, the MSE as reference electrode, and of course the platinum disc as working electrode. Then we can start the measurement. First, a little OCP, just to check if the connections are good. Then the impedance starts, going from 1 kilohertz to 1 hertz. After a little noise, we can see a straight line forming with a 45-degree angle. That's a thing that we cannot just express by putting resistors and capacitors in series or in parallel. So we need something new to explain this kind of behavior. But this is a task for the next video. See you there.